I want to talk about object-relational mapping, also known as ORM. Let me just give you some idea about where this fits into the overall picture. So by way of introduction, this is a diagram of our full stack. We've talked about it a few times, and I'm going to try to keep bringing this picture back so that you keep in mind sort of where we're working. We're starting here on the server side in the data persistence layer. So these three layers here have to do with storing application data in a persistent database. We know that we're going to use the PostgreSQL database management system. This stands for Relational Database Management System. And that's a standalone process that's going to run on a server. You could run it on your laptop if you wish, that knows how to store data persistently on disk. Now we could go directly from our application server to Postgres if we wanted to, but as we saw in the discussion about the query builder, there's some downsides to that in terms of portability and flexibility and ease of learning and that kind of stuff. So we already discussed the notion of using a query builder, that we're going to use one called Knex in here, that knows how to convert a JavaScript function call into pieces and parts of a SQL query that can then be issued to Postgres. Now that's fine and good, and we saw last time that Knex allows us to access the data in the database as an array of objects, which is convenient because we can get at the individual columns of each row by just using ordinary JavaScript, either indexing into an array or iterating over an array, and then once we have an array element, we can use the keywords based on the columns of that table to be able to access the individual data elements. That's fine, but we can actually kind of do one level better, and that's what we're going to talk about today, this idea of an object-relational mapper. And we're going to use one called Objection. The idea here is that we want to be able to convert not just from a table into some sort of generic objects in memory, but we'd actually like these to be what we'll refer to as model classes, and we'll unpack that a little bit more in a second. They're going to be sort of higher level representations of the information that's stored in individual rows in the database. More than that, the object-relational mapper is aware of things like the relationships between tables. So if we have a database that has a one-to-many relationship between two tables or a many-to-many relationship with an intermediate associative table, we can actually tell the object-relational mapper about those relationships, and it can do a lot behind the scenes on our behalf to be able to fetch information from the database using those relationships. So if we have a one-to-many relationship, say between a country and the cities in that country, as we do in the DVD rental database, we could just ask for countries, for a country by name, and then also request the cities associated with that country. And we don't have to really worry about the details of how that happens in SQL, because Objection is going to make use of Knex to create the SQL that's then going to be issued to Postgres on our behalf. That's really what we mean by an object-relational mapper. If we think about Objection's behavior from below in the stack, it's really working with relations in the sense of database tables and the relationships between those tables. But if we think about Objection from above, it's presenting that information about the relations in the database as objects that we'll see are going to actually be classes that are defined based on the underlying database structures, and we can use those classes and create new instances of those classes as objects and so forth in our code, and not have to worry about the details of how that gets converted from something that's an object in JavaScript, an object-oriented language, and what actually happens under the hood in the database itself. What are we really talking about when we're discussing object-relational mapping? Here's the kind of the secret decoder ring that gives you the details of what that actually means. So we're talking about going between a relational database and an object-oriented language, in our case JavaScript. And this table gives the mapping between the elements of the relational database and the way we're going to represent that information in our language, in JavaScript. A table in the relational database is going to be converted into a class in JavaScript. So there'll be a class that's given a name that's similar to the table in the database, and that class is going to be basically responsible for accessing the data in the corresponding table. Furthermore, the individual rows in that table are going to turn into instances of that class. So when we do a query through this model class that we're going to create, what we get back from that query is going to be instances of that class that contain the details from a single row in the relational database from the table associated with that class. So if we have a country table in our database and we define a country model class in our object relational mapping layer, what's going to happen is we're going to use that model class to access the country table. And for example, when we fetch data from the table, when we get the rows that contain information about countries, those are going to show up as instances of that class in the JavaScript representation. And then finally, the individual columns within that table, right, the divisions of all of the rows into individual attributes, are going to be attributes on the JavaScript side. And that's kind of similar to what we saw before with just using raw Knex, is that when we get a value back from the database, it's an array of objects where there's one object per row in the underlying query. And within those objects, the different attributes corresponded to the values in the columns that were part of that query. So the column itself becomes an attribute of the instance of the class corresponding to a particular value from a given column in a given row of the database. How do we configure this connection? It's quite similar to what we did when we were just bringing Knex into the picture. Using Yarn, we're going to establish a little development directory, and we need to add 3 modules. We need to have the Knex module, which Objection is going to be configured to use to generate the queries. Remember that Objection's focus is just mapping between the object-oriented language and the underlying relational database. It doesn't know specifically about SQL, and it's going to rely on Knex to do that job. We also have to have the PG package, which is the driver that allows Knex to talk to Postgres, and then Objection is going to ride on top of Knex. So that follows pretty closely the picture that we were looking at back here. So the PG driver is what talks to Postgres. The Knex layer connects between Objection and Postgres, and Objection is our object relational mapper. Before we dive into the details of Objection, I want to just remind you of the importance of doing error handling in your code. This is example code that's not using Objection yet. It's just an ordinary Knex query. So select from country. That's the simple query here, but it's not what I want to illustrate. When this, and as we said before, that's going to be an asynchronous operation because it's going to go out to the database, make a connection across the network. It's going to require access to disk. It's going to be a long-running thing, and we know that we want long-running things to be done asynchronously. When the result from that query comes back, as we've seen, we use the .then to kind of actually trigger the query itself. And when the query resolves successfully, if everything works fine, the function that we've provided inside the body of our then call is going to be invoked, right? This is, again, a fat arrow function, so the list of countries that come back from the database is going to be passed as that parameter, and in this particular case, all I'm doing is just printing out the length of the resulting query, which will just tell us how many countries there are in the database, and you can see that output down here. The thing I wanted to focus on, though, is just to remind you to always be sure to include a .catch when we're dealing with promises. And as we illustrated before, you can have multiple .thens that line up one asynchronous function after the other. And you can either put .catches in that sequence if you have specific things you want to check for along the way. But at the very least, you should include a .catch as the last method that's invoked on that sequence of promises, just so that we're always aware that something went haywire if it did. In this case, all we're doing is printing an error message to the console to let the user know that something went wrong. Obviously, that's not a very sophisticated error handling mechanism, but it's a simple way to illustrate what's going on here. So if the underlying query came up with a problem, instead of resolving the promise, it would have rejected the promise, which would eventually cause the catch method to call this underlying function. Again, this is a fat arrow function that we've defined. We're expecting an error object to be sent back up from Knex and just printing out the message associated with that. The second code snippet here is an example of forcing an error so we can observe that behavior. I'm selecting from a table called bogus, which doesn't exist. So when Knex tries to issue that query, it's going to discover that something went haywire and will end up rejecting the promise, which is going to cause the .catch to invoke its underlying fat arrow function, which is going to print the error message out to the console. And we can see here, select star from bogus is a reflection of the query that was executed, and then Postgres is telling us, sorry, relation bogus does not exist. So be sure to include those catch clauses in order to be made aware of anything that goes wrong in your database access code. All right, let's return to how do we make use of Knex together with objection. We have replicated here at the beginning of this code snippet the configuration information that we used previously to create the Knex object that knows how to write queries for our database. Again, it's going to intuit that based on the type of driver that we supply to it, and we've got to give it some additional connection information that connects to the database itself, and there'll be details on how to connect to the various databases for homework and the project as we go. So that's just what we saw before for configuring Knex, but now we want to actually layer objection on top of that. So the first thing I'm going to do is require that objection package. So just like we brought Knex into our process with this require, we're bringing objection into the process with this and storing it in a constant called objection. And as with Knex, that's kind of a top-level object in the objection package that we use to do other stuff with the object relational mapper. And we'll see that one of the most important things that we're going to want to have access to in the use of objection is this thing called a model class. And we're going to come back and talk about what that means in a second. But just for simplicity, instead of having to always say objection.model, I'm defining another constant that basically just is an alias for this objection.model class that's coming in from objection. And we're going to use that model repeatedly as we design object relational models to use with objects and objects, with Knex and objection. Now the final statement here is what actually ties together objection and Knex. So model is the main class that we're going to use from objection to be able to create this ORM layer. We have to be able to tell that model class itself how we want it to connect to our database. So it defines a method called Knex, which is designed to configure objection to use Knex specifically for that purpose. And in order to configure it, we need to pass it this Knex object that we've created up above. So this Knex object is the same one that we've been using in our Knex examples when we said stuff like Knex.select from blah. And we're basically just giving the objection model class access to that so that it can use it to do queries under the hood. Before we delve into objection models, I wanted to spend a little bit of time talking about the model view controller pattern. Some of you are probably already familiar with this or have at least heard of it, but I just want to make sure that everybody's on the same page. This is what's known as a design pattern. It's a pattern for creating software that follows certain conventions and uses certain terminology and provides us a way to communicate about what sort of application we're putting together. And it's very, very common in web application development, mobile application development. It's kind of become the sort of dominant overarching model for how we think about building applications. And I've drawn a picture of it here that just kind of shows these layers in an out of order way. But I'm going to show you in a second how this connects to our application architecture in here. So that's why it's drawn a little bit weirdly. The first thing in the model view controller model, that's confusing, the model view controller pattern is the model itself. And by model, we mean in a real generic sense, a means for storing application data. And here we're going to use a database and so forth. But the idea of a model is sort of more than just the storage details. It has to do with the way that we conceptualize the way that our application data is stored in memory, is stored on disk, interacts with other parts of our application. And we're going to see that the objection object relational mapper co-ops that model terminology to implement classes in JavaScript that know how to talk to the database itself. But in a real generic sense then, what we mean by a model is just a persistence object that knows how to turn some part of the application data into a persistent representation on disk and how to go back in the other direction to bring stuff off of disk into the application itself. Now I want to go to the opposite extreme here and talk about the view a little bit. Essentially, the view is just the user interface. It's the means by which the user receives information from the system and by which the user provides information to the system. In our case, that's going to be a browser-based JavaScript application. But again, real generically, the view is just that portion of the application architecture that interacts with the user. And then third, the controller is, as you can see in the picture here, kind of the portion of the pattern that mediates the interaction between the view and the model. In other words, it knows how to take persistent data from the model layer and present it to the view so that the user can interact with it. And it also takes input from the user and establishes the appropriate behavior in response to something the user did, which may well, and often does, interact with the model layer to either create new data in the persistence layer or to update existing data and so forth. So the controller, and that's kind of implied in its name, and again in a generic sense, the controller's job is to mediate the interaction between the view and the model, between the user and the database in a simple sense. So let's take a look at how that maps into our application architecture. So this is similar to the information I showed you previously. I've kind of restacked the application architecture here on the right-hand side. But you can see that in the model layer, we've got several technologies that we're employing. Postgres itself to store the data on disk, the Knex layer to build queries for the Postgres database, and then the objection layer that we're talking about now, which is giving us this object-relational mapping capability. Again, on the other extreme, we've got the view, and for us, that's going to be a browser-based application, of course, and we're going to use the view library, which is a user interaction toolkit. We're going to use Viewtify, which is a CSS styling kind of a library that lets us present things in a pleasant way, and then we're going to write custom code that is going to run on the browser that implements the web application. So all of those pieces constitute the view in our case. And then the controller really is this layer I've labeled happy. We haven't talked about this a lot yet, but basically that's JavaScript code that runs on the server that provides an interface to the view by way of a RESTful API. So when the application is running in your browser and you do something that requires a response from the server, there's going to be a RESTful API endpoint that's going to be provided by happy that's going to allow the view to interact with the controller. And then happy is where the controller itself. It's where the application logic is going to live. So if in response to a request from the user interface, happy has to do something with the persistence layer, it's going to go ahead and invoke something in objection to either get data out of the database or update or modify data that's in the database. So it sort of happy stands kind of in the middle here, mediating the interaction back and forth between the view and the model. Okay, so that's kind of the generic picture. And as I said before, this MVC type of architecture, MVC pattern, is super common in application development these days. And I just want you to have that context before we start talking about the persistence layer. So we're going to use this terminology model in kind of a specific sense to refer to an objection style model. So the objection package itself uses that terminology to refer to classes that capture the structure of the underlying database. But I want you to be aware of the broader context in which that term is used. Turning our attention then to models within objection, let's take a look at a super simple model. This first little snippet of code up here is an example of an objection model. So we saw previously that when we initialized objection, we were defining a constant called model, which was just kind of a little convenience reference for us to objection.model, which is the main class that objection provides. And what we're going to do in order to take advantage of all the capabilities that objection provides is we're going to use mostly the functionality in that model class, but we're going to extend it, basically create a subclass of that model class that's going to then be configured in such a way that we give objection enough information about our specific models in the database and then rely on its considerable built-in functionality to be able to access those models. And that's what's going on here with the extends keyword. That says basically that we're defining a new class. It's going to reference the country table in this case, so I've called it country, and it extends model. So it's a subclass of the objection model class. Most of the good stuff is in the objection model class, the superclass, and we're just going to give it a little bit of information necessary to configure it to point to our specific information in the database. I'm using the usual convention in JavaScript of having a class name with an initial capital letter, and use kind of the camel case convention if you have multiple words in the class name. And to start with, all we really need to do is tell the country class how to find the persistent data associated with this model. And we're familiar with the data model already a little bit, and we know that the country table is where the country information is stored. So what we're providing here is a function or a method inside of our country class that has a specific name. It's called table name. And what table name does is it allows the superclass, the model class itself, to determine which table in the database to access in order to implement the functionality of this country model. When we eventually ask the country model class to do a query for us, what the model class itself is going to do is invoke this function in order to get back the name of the database table that it needs to access to implement the country model itself. It has no way of knowing, other than us telling it, which table in the database it needs to access, and that's really the purpose of this function. Let's look at an example of how we make use of this country model class. So here's a simple query that's going to basically fetch back all of the countries in the database. So we just mention the country class that we've just defined, and it's got, by merit of the fact that it inherits from the objection model class, a method called query. And in this case, we're giving query no additional arguments. The behavior basically is going to be to do select star from the underlying table, from country in this case. So the simplest way to invoke this is the thing that runs the simplest and probably most common kind of query that we're going to want to run on our model classes. So what comes back from that query function is, as you might not be surprised to learn, a promise, right? We can tell that that's going to be a promise because we're calling then on it. In fact, what comes back from the query is, in our case, because we've configured objection to use Knex under the hood, it's actually a Knex query that comes back from the model class's query method. So we just behave like we've done before. We know that that's going to give us back an array of objects and pass that in as the parameter here to the function that we've given to our .then method. And in this case, I'm just printing out a subset of the countries from index 42 to 1 less than 44 and logging it out to the standard output. And then I've also got a catch clause in here that says if something goes haywire, just print out the error message. Again, not really doing much in the way of sophisticated error handling, but at the very least, you should be made aware that something went off the tracks. And the output that we see here looks kind of familiar. I'm printing out the individual objects by running the console.log statement several times, or a couple times. But you can see right away that this looks rather like what we saw previously with just using Knex. We've got an object here. Its attributes are the column names from the underlying table, and their values are the values for a particular row of the table and in those columns. One thing that's different here that's really important to keep in mind is that this is no longer just a generic JavaScript object. It's actually an instance of the country class, and you can tell that because JavaScript is telling us, hey, this is a country object and here's what's in it. If you go back and look at the examples from Knex, you'll see that there is no class name showing up here. It just shows you the curly brace enclosed attributes of the objects. They're just generic JavaScript objects. The fact that this is a bona fide country class means that we've now connected our business data, our application data, into the objection environment, and we'll see that that gives us a lot more power and flexibility than what we had before with just the raw Knex output of an array of normal JavaScript objects. The other thing that I'm doing here in this line of output here is turning on some debugging information that allows or that asks Knex to generate to the standard output the queries that it's running. So we can see here that the query underlying this query with no arguments is just select country .star. So that basically just says give me all the columns from the country table from the country table. Here's a slightly more elaborate example that illustrates the fact that when we're using objection and we've connected it up to the Knex query builder, we have access to all of the capability of Knex behind the scenes. I mentioned before that when we call this .query method on the country class, the model class that we've defined, we're actually getting back a Knex query builder object. So pretty much anything that we could do before with Knex, we can also do inside of objection, and then objection brings more to the table in addition to that. In this case, what I'm showing here is the ability to select specific columns, country ID and country, and then adding a where clause. And this behaves exactly the same as it does in raw Knex, because that's what's going on here. This is maybe a new version of where we're using a between query, and that's part of standard SQL, saying that the country ID column that we're trying to get, we would like its values, or like to get values, we would like to get rows whose values are between these bounds, 42 and 50. And so that's the syntax. Again, it's just a JavaScript representation of the underlying query. That's the syntax that Knex defines for doing a between query. And you can see here in the output that we have country IDs going from 42 to 50. Similar functionality as before with the .then. So when the countries are successfully retrieved from the database, we're just going to log them out. And if there was a problem, we're going to catch that and print an error message. And you can see here that, again, that we've got an array delimited by square brackets of not just ordinary objects, but instances of the country class. And that's evident by the fact that we've got this country identifier being printed prior to the details of each of those objects. Other thing that I'm showing here, again, this is just debugging output that I've turned on. We can see the query, so select country ID, comma country from the country table, where country ID between question mark and question mark. This is another example of SQL being careful to, well, actually, it's an example of Knex being careful to avoid SQL injection attacks. By just putting these placeholders in here, we're not directly constructing a SQL statement based on information that could have come from a nefarious end user. We're making it very generic, and then specifically at query time replacing those placeholders with these two values. You can see that that gets output by this Knex binding or bindings debugging output. So 42 is going to be substituted in for the first question mark and 50 for the second question mark. And again, even if these things came from the end user over the internet, and the end user can put bogus information in there that might actually try to trick the database into doing things that you don't really want it to do. By using this placeholder mechanism, the database itself, in conjunction with Knex and objection, is going to formulate a query that can't possibly do damage using a SQL injection attack. So that's another advantage of using the query builder to access the database. So far, the examples we've seen have been accessing just a single table, but as I suggested before, one of the reasons that we use an object-relational mapper like objection is that it makes it easy for us to connect the tables together in the relationships that are encoded in their primary key and foreign key relationships. So let's take a look at how we would do a many-to-one query, or how we would model a many-to-one relationship. So we've got many of one thing and one of another. Here's the ERD for the country and the city tables in our DVD rental database. We can see that we've got a primary key of country ID for country and a city ID for city. And then we've got a foreign key relationship here where the city stores a country ID of the country that it's a part of. So we can have one country per city, but a given country can have many cities associated with it. So that's what we're talking about with a many-to-one relation, many cities in one country. Let's see how we would model that in objection. Now I've got two classes showing up here. One's called country again. It's basically the same as the previous example, and it extends the objection model class. And then I have a second one called city that also extends the model class. And just like before, this first class is focusing on accessing the country table, and the second is focused on accessing the city table, but also implementing that relationship between city and country. So the first thing that's here in the city table is another occurrence of this table name method that we have to override basically here in our local class, so that the model code behind the scenes knows how to find the appropriate table in our database. So we're just telling it this is the city table, and that corresponds to the name of the table that contains city information. So entirely analogous to the table name function in the country class. The interesting part here for relations is another one of these functions that we're overriding in our city subclass that's going to be used by the underlying model superclass to know how to create relationships between these tables. Again, we're just returning some information back to the caller of this function, which is going to be something inside the model class itself. And that something that we're returning is an object that gives enough information to the objection model class to know how to navigate between the city class and the country class. So we're returning an object, as you can see here, and the object is going to have as a key country. Now, we can call that anything that we want. The fact that it's connecting us to the country class is completely irrelevant. We could call this, the country that I'm part of or something like that, but that's sort of awkward. So we're just going to call it country because that's what it's referring to. And then we're going to give some specific information to objection to tell it how to navigate from one model, the city model, to the country model. The first thing we're going to do is give it a value for this relation attribute. And this is a constant that's defined by objection. You can see that it's part of the model class itself. So it's a constant called belongs to one relation. And that's kind of a long, painful identifier name. And after using a number of object relational mappers over the years, I think this is a common issue with ORMs, is it's just sort of hard to come up with a generic way to express these relationships sometimes. And some designers take the approach of doing something very minimal, and objection kind of goes the opposite direction and gives you sort of a chatty, long, verbose way of identifying this. But the idea here is that we're saying that the city class in which we're implementing this method belongs to one relation, right? So a city belongs to one country is basically the mnemonic intent of that identifier. And then we have to say, well, which class is it related to? So the second thing that's here in the country configuration object is model class, and we're giving it the country object itself, or the country class itself, as the value there. So we're explicitly tying together this city model, this JavaScript class, with the country model, the other JavaScript class of interest here, by merit of that attribute. So we've told objection, hey, we want to have one of these countries associated with each city, and we've told it how to access that using the objection model. And the final thing we got to do is tell it how do we do the join between those two tables, because of course that's what's going to happen under the hood. Objection is going to invoke the appropriate Knex functions to join together those two tables in a select statement and retrieve the results. And what does the join look like? Well, if we go back to the data model, we saw already that the city's country ID column is the foreign key that refers to the country's country ID column, which is its primary key. So we want to tie country.countryID to city.countryID. And that's what we're saying here in this join object. Again, that's just an identifier that's used in this object. We give it a from and a to column name, and we say city.countryID and country.countryID, which corresponds to the primary key and the foreign key as we've just seen. Again, we're not telling the objection model class how to do this query, how to create the query. We're just giving it a sufficient amount of information to say, hey, there's a one-to-many relationship between, well, actually a many-to-one relationship between cities and countries, because many cities have the same country. And we're just giving it configuration data that's just the bare minimum information that it needs to be able to work within that relationship to do all sorts of interesting things, as we'll see in a second. So this is all we got to do to tell objection about this many-to-one relationship between city and country. So then let's look at a query here. We're going to query against the city model, and again, this .query statement gives us back a Knex query object that we can then refine. And what I'm going to do here is I'm going to query for a city whose ID is 45, right? So this is just an ordinary where method on Knex, and I'm trying to filter the cities that are going to come back such that their city ID equals 45. What's this first method all about? Remember that when we're talking about relational databases, it's tables all the way down. Any kind of query that you do, any kind of a join that you do, any kind of an update that you do, it's working on tables. And what we're saying here is that because we're looking for just a specific city, right? The city ID is actually the primary key of the city table. So what we're going to get back from this query, if we formulate it properly, of course, is a single row containing the information about that city. And then because we're using objection, we're actually going to get an array containing a single object that has the instance of the city class for city number 45. Now, that's what we would always expect to have happen, but because we're only asking for a single row, or a single city in this case, it's a little clunky to get back an array containing a single instance of that city class. So the first basically just says, yeah, I know I'm going to get an array back, but just give me the first one of those things. So it's just a convenience function. When we know that we're only going to get one thing back, we'll use .first to avoid having to get an array of things and then having to reference the 0th element of that array later in our code. And then we call the .then. So that's going to trigger the query. When the query succeeds, assuming it succeeds, we're going to get the city instance itself. So it's going to be an instance of that city class containing the attributes that connect to the columns in the city table. And then here I've got a console.log of city. Let's scoot down here to the output here and see what's come out so far. First of all, I've got this debugging output again. You can see that we're doing select city.star, so all the columns from the city table where the city ID equals that placeholder, and the placeholder will be bound with the value 45, which is coming from up here. And the output from this console.log at line 5 is this output right here. We can see that this is an instance of the city class, and here are all the details associated with that city. Notice that the country ID is listed here explicitly. Right? If we go back to the data model, we know that the country ID on the city is what gives us the connection to the country table. But so far, we've only queried from the city model in the underlying city table. So we haven't yet resolved this country ID to refer to the country itself. The way we do that then is once we have that city instance, and again, this is an instance of this city class, right? It's not just a generic JavaScript object, which means that it's inheriting additional capability from its superclass, which is the model class that comes from objection. And one of the things that model class implements is this weird looking function called related query. Okay, now let's go back and just refresh your memory in the fact that in the city class we defined these relation mappings, and one of them was called country. And I said that identifier could be anything you want, the country that I'm part of or something, but we've used country here as that identifier. In this related query function, you'll see that I've used that same identifier. I've got to have it as a string here because I'm not working with an object directly. But what this is saying is go to the city instance, right, that we got back from the previous query, and grab the related data according to that named relationship in the declaration of the city class. So we've got a city object, a city instance. It's defined here to have as one of its relations a country. And that country information, as we said before, has all of the details that objection needs to go and fetch the associated country for this city. Remember that there's a many-to-one relationship between cities and countries. Every city has exactly one country, so it's unambiguous which country we want to get. And that's what the related query function is going to do. And what we're doing here, so this is going to go back out to the database and fetch the related country. Now we don't have to know in our code, this is important, we don't have to know the ID of that country. We just have to sort of remind objection that we want to go get the thing that's at the other end of this relationship that earlier we defined as the country relationship. So we can see in the output that's coming next here, this chunk is actually this query that's behind this city.related query thing. So we can see now we're going not to the city table, but to the country table. And we're going to the country table where that country ID is 6. Right? So the fact that we told objection when we configured this city model about how to go from the city to the associated country by looking in the city.countryID column, for example, that's what allows the related query method to look up this value 6 from that country ID column in the city object that it previously fetched. And what's going to come back from that then is going to be a country object whose primary key is 6. And we see that that's what's printed out here by this second then clause, right? We've got one then here that says go ahead and resolve the promise regarding the query of the city table. And then that thing returns the result of another query that gives us the corresponding country. And that's passed to this then method, and we have the country that we've received. And again, we're just logging it out to standard output, which is why we see this down here. And then, of course, I've got a catch clause to deal with errors that could have occurred in either of those places. So there's a little bit of code here, but as I tried to point out before, the fact that we don't have to know kind of the details of how cities and countries are related is a win for us in terms of the software development process, because we've already told objection how cities and countries relate to one another. It can formulate this query on our behalf without us having to know the gory details of the way that the models relate to one another. So that works well, except it's a little clunky that we have to make this separate call to that related query to fetch in the additional information for the country related to this city. And we'll see that there's actually ways that we can ask for the object relational mapping layer to fetch that data in what we call an eager fashion. I want to just take a couple of minutes to talk about this distinction between lazy and eager. These are terms of art in computer science, and they get applied in a whole variety of different contexts. But in a very general way, the difference is that when we're talking about a lazy operation, it's an operation that we're trying to put off as far as possible into the future as we can, usually on the assumption that it may not actually be necessary. So rather than jumping all over it right now, let's see if we actually need this information. And when we do, if we do, we'll go and get a hold of it. And that's in contrast to eager behavior, which is where we're trying to do as much as possible as soon as we can in order to have access to whatever data that we might need immediately. And some examples of this might help clarify that. So for a lazy example on the web, when you fetch a web page down from the internet, in most cases, there's going to be a bunch of links on that page, right? A bunch of elements. And we won't actually try to fetch the content at any of those links until the user actually clicks through them, right? Clicks on a button, clicks on the link in text. In other words, we're going to wait as long as we can before we have to go back out to the network to fetch in that data. So that would be an example of lazy loading. We're not going to grab the page until the user actually needs it, and we're basically postponing it as much as possible. Or in the case of a database, what we've seen just now is an instance of lazy loading from the country's model. We got the city, and that's all that we got back from the database. We got a little bit of information necessary to fetch the country if we wanted to, because we have the country ID foreign key from the city table, but we didn't actually go out and grab the country details until the code actually requested it. So that'd be another example of lazy loading of data. In contrast, if we think about those same operations from an eager point of view, if we wanted to do eager loading of data on a website, what we could do is when the first page arrived, go ahead and find all of the places where the user might eventually click, and behind the scenes go grab the contents of those pages and cache them someplace on the browser so that when the user actually finally did click the link on the page, it immediately would be able to display that new information. So we're eagerly gathering that information right away as soon as we can so that we can leverage it almost immediately. And then in the case of the data fetching example, instead of waiting, as we did in the previous example, to fetch in the city data until our code requested it, we might set up the original query such that we're going to ask for all of the related data right up front, so that if we try to access that information, we'll have it available to us on the client right away. Let's see how that works out in practice using objection. So here's another query where we're looking for a city, and again we call this top-level query method that gives us back a Knex query object. And everything else is similar except for one line. We're asking for a city whose city ID is 45. We're asking for just the first city. We're going to print that city out when we've received it. The new thing is this line here, with graph fetched country. Now that's what triggers this eager behavior from objection. In fact, in earlier versions of objection itself, they called that function just eager. But they've kind of given some additional functionality and separated it apart so you can do these kinds of eager loads in several ways. So we're sort of stuck with this, unfortunately, kind of verbose name for this called with graph fetched. Under the hood, it actually allows us to fetch a whole graph of different related queries. So we can actually quite simply bring in a ton of additional information in response to a query. We're not going to get into that in a lot of detail, but you're certainly encouraged to check out the documentation for with graph fetched in the objection documentation to see what other kinds of cool things you can do. But basically what we're doing here is just saying, once we have that city, let's also grab the associated information from the country associated with that city. And again, that country identifier is just the name of the attribute that we provided in the list of relations between city and country. So when we run this, notice that we've only made one query, right? There's no related query thing or anything like that in here. We've only made one call out to objection. And what it does behind the scenes is it fetches the city, and then it eagerly loads the associated country because we've asked it to do that with the with graph fetched. And you can see here, in addition to the normal city fields that we've seen previously, including the foreign key to the country, it's also loaded an instance of the country and stored that under the key that corresponds to this relationship name that we provided in the declaration of the related tables for the city. And then that country has all the details, its own ID, its country name, and then the last time it was updated. And you can see that this country is actually embedded right inside the city instance. You can also see that because JavaScript is telling us here that this is actually a country instance embedded inside of a city instance, that we have all of the same access that we had before to the additional functionality that's provided to us inside of objection, because of course city and country are both subclasses of the objection model class that has this functionality and a bunch of other stuff. We've been looking at this many-to-one relationship type, and we want to explore the other relationships that are supported by objection. So let's take a look at in more detail at a couple of the other ones. Just in general, when we're thinking about models in a relation, we can kind of categorize the two model classes, which of course correspond to two underlying tables, in terms of the source relation, sort of the model that contains that function relation mappings, and then the related relation, which is the model at the other end of the relation. I mentioned before that sometimes object relational mappers have kind of goofy names for how they talk about the relationship between these two tables or the two relations. And this is kind of a way that I use to sort of keep these terms straight. So when we're trying to create that relation mappings function that configures a model class to know about other models that it's related to, when we're writing that function, we can think of that as the source, and then the thing at the other side of the relation is the related model. So if we take a look at the one-to-many case, we can see here that on the source side, we would use belongs to one relation, right? That's pretty much what we just did with the cities and states, because a city belongs to, cities and countries, because a city belongs to one country. We were writing code in the relation mappings of the city, which made it the source, and then on the other side we had the country. Now, if we wanted to be able to if we wanted to be able to refer to the cities that were part of a country, we would also have to create relation mapping or a relation mappings function on the country side as well. And in that case, we would refer to the relation as a has many relation. Similarly, if we have a many-to-many relation, well, we're going to then use a different identifier to indicate the relation type called many-to-many relation, and we actually use that to specify the join table or the associative table that has the two foreign keys that refer to our two tables that are joined in a many-to-many relation. And we also have a one-to-one relation that's supported. I find that in practice, one-to-one relations are not super common, but they are definitely supported by any object-relational mapper, and objection is no exception. So if we're talking about the source side, we use belongs to one, and if we're on the related side, we say has one relation. And then we can also have a one-to-one relation that has additional data that's captured in an intermediate table, and we would use that, or we would use has one through relation to specify that join table. So again, the most common that we're going to encounter are the one-to-many relationship and the many-to-many relationship. And as I've been suggesting here, we need to be able to create this relation mappings function wherever we want to be able to refer to a related model. So again, when we defined our country table our country model previously, all we told it was the name of the table. We didn't add any relation mappings to that class. Whereas in the city class that we inherited from model, we defined both the name of the table and the relation that takes us from the city to countries. Now, just with that, we can start out at a city and ask for the associated countries, but we can't go the other direction easily. Instead, what we would want to do if we wanted to navigate from countries to its cities, we would go into the countries relation and define a relation mappings function there that gave objection the sufficient information to know how to formulate a query from a country to get to its associated cities. So you only get kind of one direction of the relationship when you add a relation mappings function. If you want to go both directions, which is totally fine, you just have to define the corresponding relation mappings on the other side of the relationship. So let's see how we would do that with the cities and countries. We're again looking at a one-to-many relationship. We looked at many-to-one previously. That was the thing that connected our cities, our many cities to one country. We're going to go the opposite direction now and look at the one-to-many side. So now, although we could basically reuse the city model class that we had previously, I thought just for completeness I'd show this here. And I've left out the relation mappings function from the city table that I defined before, because we're really focused now on starting at a country and being able to list the cities that are in that country. So I still have to be able to tell objection what table to find the city's information in, and that's what this function is doing. And similarly on the country model class, I'm going to do the same or a similar thing that points to the country table. But the interesting part here is the other side of this relationship, where now I'm saying if I'm a country, I want to be able to refer to my cities. And notice that I've made this attribute, again, we can call this attribute anything we want within reason. But what I normally do is if I'm creating an attribute in a model class that refers to a single thing on the other side of the relationship, like when I'm on a city and I want to get my one and only country, I'll give it a singular name. So that attribute I'd called country that we've been looking at so far. In this case, I've got a country, and I want to be able to look at the cities that are in that country. And I know that that's one country to many cities, so I'll name the attribute in the plural in this case. I've also got to use a different relation type, right? So back to this table, instead of saying belongs to one relation, I want to say has many relation, because a country has many of the other thing. It has many cities. So here's where that shows up. I also need to tell objection the name of the class, and actually this is the class instance itself of the other side of the relationship, and I need to give it the join information. And this is basically the same two columns that I'm showing from the other side of the relationship. Again, there's not anything in objection that tries to intuit these column names or anything like that from the other side of the relationship. It's up to you to configure them. There are object relational mappers that try to do they try to be smart about that and kind of allow you to really minimize the amount of information you have to share, and it tries to interpret what you've put to do things like intuit the other side of the relationship. I've found that in many cases, those are kind of more trouble than they're worth because they don't behave super deterministically or super obviously at times. And I'd prefer personally to just have to put in a few extra fields to make it explicit what that relationship looks like. So anyway, now we have the ability to start with a country and fetch up the cities that are in that country as far as our database is concerned. So here's an example of a query. Now we're starting from that country class, running the query method, which is inherited from Objection's model class, the superclass of our class. We're fetching a particular country by its ID. Again, I'm getting the first such country because I'm only asking for one country. And then here's the non-eager version of this, right? When I get the results from that first promise, that first query promise, I'm going to get back some country information if everything worked. I'm going to log that out to the console, and then I'm going to do the related query. And again, I'm passing in the name of that relation mapping as the argument to related query so that Objection knows what to do with that. And it's going to return another promise that is going to resolve to the result of this query. So I've got another then in series here that's going to end up with this list of cities. And again, I'm going to console log that. And I've, of course, included a catch to handle any errors that come up. Now the output then, so the output from this first console.log is the country. We can see that country ID 17 is Bulgaria. And then the related query is going to give us back the countries that are related to Bulgaria. Again, because it's a one-to-many relationship, there's going to be more than one, or potentially more than one country, so it's going to give us back an array of those of those cities. And that's what we see here in the next section of the output. We've got an array with the square brackets, and inside of this are two city instances that correspond to two cities that are in Bulgaria. And you can see that they have country ID foreign keys that have 17s that refer to the country itself. And as before, this is a country instance. This is a city instance. It's not a generic JavaScript object. It's a specific instance of that model class. So this would be the lazy loading version of this. We don't fetch the cities right away. We might not want them all. Maybe we're just trying to list all the countries in our database to allow the user to select them. And in this case, that's what's happening. We wait until later to fetch the cities associated with a given country. We can also do this eagerly, as we did when we were looking at the opposite relationship between cities and the associated country. We're going to use, again, the query is essentially the same, except we've got now with graph fetched of that cities relation mapping. So behind the scenes, when Objection is grabbing this country, it's also going to go and fetch in the cities associated with that country as defined by this relation mapping. Still constraining this to be a single city. We're only going to get the single country. We're only going to get the first one, and then we're just going to print out that object. Notice that we don't have to have chained then statements because we are getting everything back that we want by merit of using this eager loading with graph fetched method. So the return value is just the country object, but it has embedded within it a cities attribute, again, corresponds to the name of the relation mapping, and that's an array that contains the two cities that are in the database part of Bulgaria. Okay. So we get everything all in one request to Objection. It goes out to the database, does its thing, and assembles the results back together in a very convenient way for us to use it in our application. Finally, let's take a look at the many-to-many relationship. So I've got one thing that can have many of the other things and vice versa. We'll use films and actors from our dumb little DVD rental database. So we know that a film can have multiple actors and an actor can appear in multiple films. And in order to support that many-to-many relationship, we need to introduce an additional table called an associative table usually. And its main job is to basically just connect a particular film to a particular actor. So the film has a primary key of film ID, actor has a primary key of actor ID, and film actor has two foreign keys. These are both foreign keys. One that refers to a particular actor and one that refers to a particular film. So in order to associate a film with an actor, we create a new row in this film actor table that has the associated actor ID and film ID. And that allows us to come up with any combination that we'd like of films and actors. So we can have as many films for an actor as we want, as many actors in a film as we want. So we need to do some more work here, obviously, to do this join. In the previous examples, we're just joining together 2 tables. Now we're going to do a 3-table join. All right, so we can, in fact, leverage Objection to help us with that process. So here is our actor model class. Again, we're extending the superclass that's coming from Objection. Actors live in the actor table, so we have to have a table name function. We'll come back to this full name here in a second. And that's all I'm putting in on the actor side. Then I've got another model class here for film, which also extends the Objection model class. I've got to tell it the name of the table is film. And the interesting part here comes as we specify relation mappings. So for a film, what I want to do is have a way to fetch the actors that are in that film. Again, because that's going to be a many thing. A film has many actors, an actor has many films. I'm going to give the name of this relation mapping a plural name. So I'm going to say actors. So I want to get the actors for this film. The relation type now is many-to-many relation, and that's actually the thing that we're going to use on both sides of the relationship. If we wanted to extend the actor model to be able to fetch back all the films for a particular actor, we would also use a many-to-many relation type in the relation mappings function. We have to tell it that we're going to fetch information from the actor class, and then the join gets a little bit more elaborate here. In the previous examples, the join only had to specify the foreign key on one side and the primary key on the other side. Here, because we've got 3 tables involved, we need to not only specify the keys on the from side, the film's film ID, and the to side, the actor's actor ID, but this additional attribute here called through is what we're going to use to specify information about this table that we're going to go through in order to be able to connect films to actors. So the through also has a from and a to, and here we're saying filmActor.filmID and filmActor.actorID. So those 2 fields, those 2 columns are these 2 columns, right? FilmActor actor ID, FilmActor film ID. And with that information then, Objection has sufficient data about our data structure in the database to be able to construct queries that will join together film and film actor and actor to be able to fetch lists of actors for a film and satisfy this relation mapping. All right, so let's take a look at how that looks. Again, because we've defined these relations on the film side, that's sort of where we have to start our query. If we want to be able to go in either direction, as I said, you'll have to do the moral equivalent of this relation mappings function over here on the actor side. But we've just done it on one side. So I'm going to grab the films, and I want to get the film ID and the title of those films. So again, the query method just returns a Knex object that's kind of pre-configured in a way to know what it's going to connect to in the database. But you can use almost all the same things you can use with an ordinary Knex query on this object. So I can choose particular columns to select. I can choose a particular film that I'm interested in by film ID. I'm only asking for one film, so I've included the first function here, or the first method. And what I'm going to get back then is a film together with its actors. So here's the film object that is going to be passed to me if the query promise resolves successfully. And what I'm doing is printing out the film's title with a title header, and then I'm going to get the actors for that film. So just like in the previous examples, we can do this in a lazy way or in an eager way, depending on whether we need the data right away or whether we can wait for it until later. So I'm doing the related query, and the value passed there is just the name of that relationship that I defined back here. Once that resolves, this console.log is going to output this line. It tells us the name of the film that we're querying, film number 17. And then the related query is going to run, and what it's going to do is use the information from this relation mappings function to bring back the actors associated with that film by doing the 2 joins and the ons and all that stuff. When that succeeds, it's going to satisfy the then method defined on the promise returned by this second query, and then I've just got a little iterator here with over the array of actors. I'm going to do just the minimal of formatting here. I'm going to iterate over that actor array, and for each of the actors I'm going to print out actor and then actor full name. And you can see here that the remainder of these rows are what are coming from the second then method. I wanted to say something about actor full name. If we go back and look at the actor table, we'll see that there is no full name attribute in this table. So where does that actor full name come from? Well, we kind of skipped over it before. I've actually defined it here in the actor table. Again, because these are bona fide JavaScript classes, we can add methods to them that have access to the content of the underlying database data. So for convenience, because my database only has a first name and a last name field, if I find myself creating a lot of reports or a lot of output that need the full name, it might be simpler for me to just define that once and then use that function. So I've defined a function, a method on this actor class called full name, and it uses the this variable to refer to the data that was loaded from the database to instantiate that particular instance of the actor class. So I'm grabbing this.firstName and I'm appending it to or with this.lastName and returning that string. I should in here have used backticks and the $curly syntax, but I guess this was older code. The point is, though, that I can now give this actor class additional functionality that's going to be shared across my entire application. Anytime I want to have an actor's full name, if I have that actor class instance with that actor of interest, I just call full name on it. So you can define as many additional kind of helper functions or reporting functions or counting functions or whatever on these classes because they're just regular JavaScript classes, which can be really, really helpful to abstract out specific pieces of functionality that you want to be able to reuse. So that's where that comes from, and you can see we're getting the actors' first and last names. Finally, this was, of course, a lazy query. We can also do an eager query. So same basic parameters. I'm going to get the ID in the title. I'm going to get the film ID. I'm going to select by the film ID. And now I'm going to do my eager fetch with graph fetched from actors. And the result of that is going to be a single film instance or object that's going to contain an actors attribute that will itself have an array of actors stored in it. And you can see here that I only have to, obviously there's only one query going on or one promise that needs to be resolved from the objection library, and I'm going to get as an argument here that film, and you can see here I'm just going after film.title. And then because the actors on that film are going to be stored under this actors key within the film, you can see here that when I do this iteration to print out the actor's full name, I'm iterating over film.actors and then using the standard for each. So within that film object, objection will have added a new attribute called actors, which it will fill with an array of actor objects that I can then access like I did before, and you get the same output. So that's the eager version of the query. Here's some links. There's some more information about object-relational mapping on the Wikipedia. If you want to take a look at that article, it's not super great itself, at least the last time I looked at it, but it links to other resources. If you want to learn more about objection, it was originally introduced under the not-so-delightful name Moron, but there's a pretty good blog post about kind of what goes on under the hood in objection that's linked there. And then the objection reference documentation is really nice. In the last, 9 or 10 months, the author of the package has updated all the documentation, so it's a really nice, pleasant format to read, tons and tons of great examples, and it's got some really nice searchability. So as with the Knex documentation, when you're doing an application that uses Objection, Knex, Postgres, almost always helpful to have open in your browser, right, a tab for the documentation for each of those three so you can refer to it easily.